Everybody, and welcome to this semester's rendition of 61C, the course formerly known, or actually still officially known as Machine Structures, but what we've been calling lately Great Ideas in Computer Architecture. Can you guys hear me in the back? All right, a couple people can. Okay. All right, so you're in for a special treat this semester because you have not one professor, but two. And my name's Mike Franklin. I'll tell you a little bit about myself in a second. Our other instructor is known to most of you guys, Dan Garcia. Let's hear it for Dan. Yeah, okay. All right, so what we're going to do today is, I'll tell you about myself. So the first thing you've got already is Homework Zero. And Homework Zero is to tell us a little bit about yourselves. And I didn't actually read Homework Zero, so I'm not sure the format's the exact same. But, just basically, I'm from the East Coast. Through a long story that we don't have time for, I ended up getting a PhD at University of Wisconsin, which you'll see is an important fact later in the lecture. I've been here since '99. I'm a database guy. I usually teach database classes. This is my first 61X class. Bear with me. Dan's helping me out, actually doing most of the work. When I'm not teaching, for research, I run something called the AMP Lab, the Algorithms, Machines, and People Lab. It's a project on making sense of big data using cloud computing and other technologies. And so it's pretty relevant to this class, so we'll be weaving in some things about that kind of technology throughout the semester. I just got this kind of cool award that the CS graduate students gave me for being a good advisor, so I was happy about that. I've done a startup, so if you're interested in those sorts of things, I can tell you mostly what not to do, but I can give you some advice about that. And I'm not only a producer of Berkeley education, I'm also a consumer. I have a son who graduated here a couple years ago, so I sort of got to see this experience through his eyes, and it was pretty interesting to watch that. So that's a little bit about me. Let me tell you about the class. So today, tell you a little bit about what we mean by machine structures, and then I'm going to focus on these 6 great ideas on computer architecture. So there's sort of themes that we're going to emphasize during the class. Some of them we're going to focus on. Some of them will just sort of be kind of an undercurrent throughout the semester. And then I'm going to hand over to Dan, and he's going to tell you how things are really going to work. So, and then most of the lectures during the semester, it'll be one of us or the other. Maybe every once in a while we'll do a joint lecture like this. Oh, okay. And Dan has informed me that, as you guys probably expected, we'll have the slides online for you guys. And isn't there supposed to be a slide cast or something? Oh, yeah, this is being, yeah. So it's a screencast. So you get to see the slides, you get to hear the presentation, and you don't have to look at the professor. So maybe that's a better way to do it. I don't know. It's up to you guys. All right, so let me jump into this. So, all right. A lot of people think about 61C as a C programming course. That's really not what it's supposed to be, although one of the useful skills you do pick up in the class is how to program in this language called C. So the course is really about kind of where the software meets the hardware. And the idea is that although on a day-to-day about a lot of these details all the time, in order to be a proficient software engineer, you really have to understand enough about the underlying hardware to be able to make good use of it. Okay, and so that's really what we try to get across here. It's to teach you enough about the hardware so you can be a more effective software person. The reason we use C, even though it's kind of an ancient language, is because it is pretty close to the hardware, especially compared to other languages you might have seen, even Java, but certainly things like Python. When you're working in C, you're really forced to think about some very fundamental things in terms of memory, in terms of processors and threads and things like that. So, that's really why we cover it. So you will learn C as a byproduct of this. In 186, the database class, we actually do projects in C. I think it's the only upper division class left that we do that. So I have a personal interest in making sure you guys know C so that when I see you next year or the year after, we don't have to teach it again, right? So that's what we're going to do. All right, so So this is the way 61C used to be taught, and this is kind of a goofy picture. The picture, you probably can't read it. It purports to be a prototype of a home computer, But it's actually a pretty well-known fraud. I mean, it was actually I think it's actually a submarine, a mock-up of a submarine control something. But anyway, the idea is that, computers used to be big. Now they're not so big. And this is supposed to be new school, but I didn't have time to find a new picture. So it's kind of new school. And if you can read that, that actually says singular. I was a little embarrassed. That's what AT&T used to be. Anyway, don't let that bother you. But the idea is that, computers have obviously become incredibly powerful, incredibly small. Most of us carry around a fairly sophisticated computer with us all the time. Most of us, even when we're in lecture, although we're tempted to look at that sophisticated computer to do email and Facebook and text and stuff like that, we're not doing it, but we could be. So, we all understand that. The other part of the story, though, is that on the other side, so computers have gotten really, really small, but they've also gotten really, really big in a different way. So this is a picture of a container that's sitting behind Soda Hall. So how many people have seen this out near the volleyball court? Okay, so does anyone know what's in there? Did anyone ever guess what was in there? Yeah, a whole bunch of servers. Did anyone have any more creative guesses than that? Gold, yeah, that's where we keep the gold. And it's also where we put the bad graduate students. But anyway, it's a server, but it's a server that's connected in a very tight way. And so it's actually a big computer, okay? And that's really just a little instance of something that's going on out in the world where computing is moving kind of away from individual servers and individual desktops to these two extremes. So on one extreme, you have the personal devices that you tend to carry around with you. The other extreme, you've got these massive data centers, right? So sitting behind all your favorite web services, whether it's Google or Facebook or what have you, is a huge, or actually a bunch of huge data centers. And so that's what this is a picture of. You can see it on probably when you download the slides better. But the idea is you just take this thing and you multiply it times 100 or 1,000 or 5,000 or however many you need. Okay, and so the whole building is really a computer. And we'll talk about this a little later in the semester, but actually where a lot of the data center work is going is you finally realize you don't need the building. So you just get rid of those and you just have sort of parking lots of these things. And that's what people are starting to deploy. Okay, so bottom line is that you used to have the luxury when you took a class on machine structures of thinking about a single machine, right? Down here you have all the hardware, up here you have the software, and then our focus is on where those things meet. But you're not going to be able to get away with that anymore. Okay, so this class is going to cover a lot more kind of ground because we have these kind of extremes of computing, the small stuff and the really big stuff, and not that much in between anymore. Okay, so what does that mean? Well, okay, if you start looking into one of these things, what you see is rack and racks, rack after rack after rack. Each rack has server, 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 server. Each server has a bunch of processors on it, and each processor has a bunch of cores. Okay, so each core is its own little processor. So it's got the functional units, the arithmetic, stuff for instructions, and so on. Okay, and then that's made up of logic gates ultimately. Okay, and that's on the hardware side, and on the software side. What you need to be able to doing is you've got all these resources, right? So you've got thousands and thousands, you've got hundreds of racks, you've got thousands of servers, you've got tens or hundreds of thousands of cores, okay? And those cores are made up of however many millions of transistors. And if you use each of those one at a time, then you just wasted a lot of money, right? Because while you're using one, nothing else is going on. So the only way to really make this thing work efficiently is to get it all working at the same time. Okay? So on the software side, it's really about parallelism. So, million search requests come in. You don't want to run them one after the other. You want to run them all at the same time. Okay? You want to take that work, individual job, and split it into little pieces and run those at the same time. Okay? Individual instructions, actually, you can run instructions in parallel too on a single core. There's lots of data, so you'd like operations that operate on multiple pieces of data instead of just one. And I forget what the other one is. Oh yeah, you want all the sort of the little electrons flowing as much as possible, under here, right? So that's kind of what we're setting out to do in 61C this semester. And just to give you a little bit of a roadmap, and Dan, I don't know if you've seen this build, so correct me if I'm wrong, but Project 1, we're going to focus sort of on, almost sort of the good old style 61C, where you've got a processor and you've got memory and you've got I/O and you're trying to get that all to work together. Project 2, we're going to jump up to the data center and we're going to do a MapReduce project, hopefully on a real cloud infrastructure. Project 3, we're going to look more at sort of data parallelism and how to take a big single computation and break it into pieces and get it to run really fast. And then the fourth project is the good old logic simulator. So you actually get to play around with logic gates. And, I last looked at that stuff many years before any of you were born, so we'll all be learning that again together. All right, so that's the map of the class. If you want to leave now, that's what you're signing up for. Okay. And Dan will tell you, if you all want to stay, I think we're cool with that too. So you'll hear more about that later. And I hope you do stay. But if you don't like that, now's the time to give somebody your seat, okay? All right. So what I want to do now is sort of give you the big picture, and then we'll go into details later. Okay. So what are the great ideas in computer architecture? So last year, two of the other faculty members, Dave Patterson and Randy Katz, decided they wanted to redo 61C, and they built it around this idea of big ideas in computer architecture. You'll recognize at least Dave Patterson's name. He's one of the authors of our textbook. And so the idea was, rather than teach kind of individual pieces about how machines work, let's take a step back and let's try to generalize some big themes, okay? Now, it's interesting. In fall, they had 5 great ideas. In spring, they had 6 great ideas. Dan and I haven't really thought of any new great ideas yet, so we're still sitting with 6, but, we might come up with 1 or 2 new ones. And if you have any suggestions for great ideas, by all means, let us know, okay? But these are the great ideas, and I'm going to go through them sort of very quickly, one by one. Okay. All right, so great idea number 1 is this idea of having a bunch of different levels of representation, okay? And basically taking one level and then kind of translating from level to level to level, okay? So sometimes this is known as the turtles all the way down phenomenon. And basically where this comes from was somebody famous, Wikipedia said it might have been Bertrand Russell, was giving a talk, mentioned the fact that people used to think the world was flat, but now we all know that it's not, and that the planets rotate around the Earth. Somebody came up to him after the talk and said, what's that? You don't think it's Bertrand Russell? No. And said, well, that's not true. You know that the Earth is actually sitting on the back of a large turtle. And Bertrand Russell said, but, what's that turtle sitting on? And the person said, well, oh, you think you're clever, but everyone knows it's turtles all the way down. So that's what that is. That's turtles all the way down. So that's kind of what we're doing. We're going from level to level to level to level to level. So does anyone know so we start off at what we like to call a high-level language. Other people might say that C isn't such a high-level language. But that's C. Does anyone know what that little code snippet does? It's a swap. Okay, great. So you want to do it. So up in your brain, you have the idea of swap. You turn that into C. That gets compiled into assembly language. Here's an example of MIPS assembler that's the language, the assembly language we're going to study, or at least use in this class. That gets turned into machine code, which is actually bits, and then that gets translated into the hardware, okay? And so, the cool thing about this class, or one of the cool things about this class, is we're going to do that whole stack, okay? So by the end of the semester, you'll have had experience with every single one of those levels and the translation from the level above it. Okay? So that's idea number 1, which is you hide just outrageous complexity by building, better and better abstractions on top. Okay? And you just, keep raising the levels of abstraction. Big idea number 2 is Moore's Law. And Moore's Law basically says that the number of transistors you can put on a chip doubles roughly every 2 years. Okay? So if you look at, these were the very early microprocessors, the Intel 404 and 808, and this is a log scale, and you look from the early 70s to now, and you can see, basically Moore's law has held pretty well, even out to some of the latest and greatest technologies. Okay, so that's why we went from the submarine where somebody could credibly say that submarine control mock-up was a mock-up of a home computer to what you can carry around in your pocket. That's totally Moore's law. Okay, and then you take each of those really powerful pieces and you scale those out. All right, so Moore's law, and this is obviously one of Dave Patterson's slides. He's a big Bears booster. And, he wanted you to make sure that you knew that Gordon Moore was a Cal grad, got his bachelor's degree here. Not in computer science, because we didn't have computer science back then. Okay, so that's big idea number 2. This is a lead up to big idea number 3. This isn't big idea number 3 yet. So this is Jim Gray. He's another Cal alum. Actually, the first person to get a PhD in computer science from Cal back in 1969. Won the Turing Award, which is basically the Nobel Prize of computing. And Jim did a lot of work on database systems. And he came up with this analogy to sort of give you a feel for what it's like to live in a memory hierarchy. Okay? So basically over here is sort of the computer memory hierarchy. So the very fastest thing is registers. If you need to go to the on-chip cache, that sort of takes twice as long as getting it out of a register. If you need to go to onboard cache, so off the chip but on the board, that's another factor of 5. If you need to go to RAM, that's another factor of 10, right? So 100 times slower than registers. If you need to go to the disk, right, which is this mechanical thing that's spinning around, okay, and moving an arm back and forth, it's crazy. That's 1,000,000 times slower than getting the data out of the register, and so on, okay? So in order, the problem with computer science, or one of the problems is, you're dealing with these vast differences. You talk about order of magnitudes like other people, talk about, having, 25 cents in their pocket, right? So you say, oh, yeah, that's 6 orders of magnitude, right? Well, what does that mean? So he basically came up with this analogy. He said, okay, let's say you ask me a question, okay, and I know the answer, and I can think of it. Let's say it takes me about a minute to figure it out and give you the answer, okay? Well, that's equivalent to getting the answer out of a register, okay? If I don't know the answer, but I can walk over to the library and look it up, okay, maybe that's going to take 10 minutes, right? Okay, so going to the onboard cache is like, well, I don't know the answer, but I can walk over to the library to look it up. And then it just gets worse from there. The equivalent of going to memory for a computer is, for us, driving to Sacramento and looking it up there. And if you have to go to disk, well, the equivalent in people time is you get on a spaceship and you go to Pluto. Okay? So every time you do something in the processor that causes a miss, that's not in the register, it's not in the caches, it's not even in memory, you got to go out to disk and get it, put on your space suit and head off to Pluto. Okay? That's what it's like to the processor sitting there. Okay? So this was Jim Gray's, he got the Turing Award for other stuff, right? But not for this, but I kind of like this analogy. And by the way, he gave this talk at Berkeley, that's why I like it. That's why Sacramento is here. Okay, so what's the big idea number 3? So big idea number 3 is this idea of a memory hierarchy. So down at the bottom, so this is the inverse of Jim's picture. But at the bottom, at the top, you've got the CPU and all the storage that's close to it. And then as you go down here, you go to memory, solid state memory, out to disks and so on. Okay? And as you go down this hierarchy, things get slower and slower and slower by the scale that we were just talking about. But they get bigger and bigger and bigger, okay, because they're cheaper. So what's happening is down at the bottom you have huge amounts of really slow memory, and as you go up this thing, you get less and less faster memory. And it's purely economic. It's just that this stuff's really expensive per bit. This stuff gets cheaper and cheaper per bit. So the trick, so that's one part of the idea, but the real big idea is how you use this thing, okay? And that's this idea of locality. So if every request you made up at the CPU had to go all the way down this hierarchy, it wouldn't save you anything. In fact, it would be probably more expensive. You'd be better off getting rid of some of these layers. The only way this thing works is if once you bring something up a level, you're likely to use it again. Okay, so that's the idea of locality. And there's 2 types of locality. We don't have to worry about this too much right now. But there's temporal locality, which says if I've used something recently, I'm likely to use it again soon. That's temporal. And the other is spatial, which says, you know, if I use this piece of data, I'm probably going to use something that's physically near it. So that means, you know, when I read stuff from the disk, I shouldn't read a single byte. I should read a whole bunch of bytes. Because if I'm going to use this byte now, I'm probably going to use the one next to it next or soon. Okay? So that's why memory hierarchies work. Because as you're bringing stuff up level to level, you can keep less of it, but it's more valuable stuff. You're more likely to use it. Okay? So that's big idea number 3. Okay, so we're halfway done with big ideas. All right. Big idea number 4 is a real big one, parallelism. And parallelism is going to show up a bunch of places in this class. This is instruction parallelism. So, you know, you have this classic fetch, execute, store cycle. So each instruction, you got to get the instruction, you got to find its data, you actually run the instruction, and then you got to store the result. Okay? And instruction level parallelism, parallelism says, you know, if you could get a bunch of these going at the same time, then you can get a lot more work done. So for example, in this type of a pipeline scheme, at time 3, you're executing the first instruction, you're finding the operands for the second instruction, and you're finding the instruction itself for the third one. And you're doing that all at the same time. Notice it's all using different parts of the hardware. So why not? Okay, so we're going to spend a bunch of time talking about this kind of parallelism. Moving up a little bit, there's another kind of parallelism where you have an application or an algorithm. You figure out that parts of that algorithm don't depend on each other, so you can run them at the same time. So you do this thing called a fork, and then you split it into threads and let those threads run concurrently, and then you gather up the answer, and then you got your answer. Okay, rather than doing this one, then this one, then this one, then this one, then this one. Okay? This stuff is where you're going to get the big speed-ups from having all that hardware around. But as you can imagine, conceptually, it's a lot more complex than just running things straight through. Okay? So that's another kind of parallelism. Moving up even higher than that, you can have sort of inter-job parallelism. So this is just, is just an example of you have sort of 3 separate jobs. If they don't depend on each other, you can send them to 3 separate processors. In this case, 3 separate people. They can do them at the same time. Okay, so we had parallelism at the level of instructions. We had parallelism of a single job by breaking it into threads. And then this is kind of even coarser-grained parallelism, just saying I have lots of jobs, I can run them at the same time. All of those techniques are super important for getting good performance. Okay. Unfortunately, in addition to complexity, there's another little thing you got to worry about, and that's called Amdahl's law. Okay? And this is where the Wisconsin thing. So he didn't make it to Cal, but, you know, he's probably like me. He didn't get into Cal, he got into Wisconsin, so he went to Wisconsin. So, you know, don't let my Wisconsin friends hear that one. So here's what Gene Amdahl said years and years and years ago, probably shortly after he got his PhD, or maybe during his PhD. You know, people are all excited about multi-core, right? You used to buy a processor, it'd have 1 processing unit, right? 1 core. Then it started having 2, right? That's the Core Duo. Or does the Duo have 4? I forget. The Core 2 Duo. I never understood that. Is that 2 cores or 4? Anyway, 2 cores, then 4 cores, then 8 cores, then 16 cores, okay? And if you think about it, you say, wow, things are just going to get faster and faster and faster. Every time I double the cores, right, I'm going to get, you know, a speed up. I'm going to get another factor 2 speed up. And what Gene Amdahl said was, you know, geez, you know, it turns out that's not true. That if you think back to this picture here, you'll notice this is the whole job, okay? This part can run in parallel, but this stuff can't, and this stuff can't, okay? So what Gene Amdahl said was, if you think about your problem as the piece that can be run in parallel and the piece that can't, then the thing that's going to limit your performance increase as you add processing units or parallelism is you're going to be bounded by the piece that you can't parallelize. Okay, so that's what this little equation here says, right? So if x is the percentage of the job that you have to do serially, you can't split across multiple units, okay, then your speed up is kind of bounded by this. So if 10% of your job is serial and there's nothing you can do about it, then the most speed up, if you make this part go to zeros, right? So n is going to go to infinity. You have an infinite number of processors. basically the maximum speed up you're going to get is about a factor of 10. After that, you're done. Okay? If half your job has to be done in serial, you can only get a factor of 2 no matter how many processors you have. So that's what this is showing, that as you're adding cores, you'd like to think you're getting performance benefit like that, but you're not. Depending on the job, you start seeing this decreasing benefit of more and more processing. Okay? So that's something that we're going to have to wrestle with as we're thinking about making instructions run in parallel, making threads run in parallel, and making jobs run in parallel. And unfortunately, it was a guy from Wisconsin that came up with that bad news, but there you have it. That's a law. You can't violate that. That's why it's called a law. Okay, we're almost done with great ideas. Another great idea is that you got to measure your performance, and then you're going to improve your performance. And so, the tricks we're going to use to improve performance are the ones we've just talked about. Locality, right? We're going to try to improve locality, so we're not going out to Pluto every time we need a new piece of data. Okay, we're going to use parallelism, right? For the happy part of Amdahl's equation, we're going to try to make that go as fast as possible. And we'll talk about other types of hardware that you can use to speed up specialized, types of calculations. Okay, so idea number 5 is performance measurement and improvement. And why is it measurement and improvement? Well, in order to improve something, you got to measure it, right? Or at least to know whether you've improved it or not, you got to measure it. So we're going to do both those. We're going to measure performance. We're going to improve performance. Okay, big idea. Oh, okay, this is the lead up to big idea number 6. And there's only 6 so far. So failure. So far we've been talking about this happy world where things get faster and faster and faster. And if we're smart enough, we can make things run in parallel, and they're going to go even faster. But there's a problem. And the problem has to do with failures. So we don't have clickers today. We'll talk about that in a little bit. But if we did, we'd use it on a question like this. So let's say you've got one of these big warehouse scale computers, right? One of these big data centers. You got 50,000 servers. Each server has 4 disks. Okay? And let's say on average, there's a 4% chance that over the course of a year, any given disk is going to fail, right? So any disk, 4% chance is going to fail during a year. So 50,000 servers, 4 disks, 4% annual failure rate. You as the person running that data center or trying to run your job in that data center, how often do you have to worry about a disk failing, right? So once every month, once every week, once every day, once every hour. Anyone brave enough to hazard a guess? Yeah. Once every hour. Okay. So if you're running a big data center, just with these simple, back of the envelope calculation, here's what's happening. You got 200,000 disks. 4% of them fail during a year. That means every year 8,000 disks fail. Okay. Well, how many hours? This was actually the most amazing thing to me about this slide. Is actually this. I didn't realize there were only that few hours in a year. That's really changed my attitude about how I spend my time. Okay? But anyway, there's 8,000 and some odd hours. So basically it just fails every hour. Right? So that's the other problem with this idea of parallelism. Right? You got Amdahl's law, okay, which restricts the benefit you're going to get. And then as you have more and more pieces, the more likely they are to break. Okay? So yeah. So what we're going to do there is we're going to do redundant processing. So here's a misbehaving processor, but if we vote, we get the right answer. So 1 + 1 = 2. And then also, even in terms of storage, so things like RAID, where you've got data stored across multiple disks, you can use redundancy across those disks so that if any one of these disks fail, you can still get your data. Okay, so we're going to talk about redundancy at the level of a data center. So if one data center fails, you can still use others. At the level of disks, yeah, like the hurricane that's about to come up, or in the Amazon. I shouldn't say bad things about Amazon because they're going to give us credits, I think. But the Amazon failure where one data center failed and other people weren't necessarily able to get their work done. We'll talk about that when we get to that part. And then also even at the level of individual disks and individual, in a processor, in a memory, where if a single bit flips, you can recover from that. So you want to recover from bits flipping, from disks failing, from computers dying, and from Hurricane Irene. Okay, that's great idea number 6. Okay, so with that, I'm going to hand it over to my co-teacher, Dan.
Let's give a hand for Mike, huh? All right.
All right, you know how to... Yep. You have to give me the handout. Yeah, perfect. Okay, wonderful.
Yeah, we're all set. All right, hi everybody. This is great. Well, that's the first time seeing your faces. I only was looking at Mike the first part of half of this. It's great. We've packed the room. That's great. So this is an experiment in progress. I've been teaching 621C for quite a while, but this is the first time teaching the new 621C, right? The one with the iPhone and the data centers and stuff. So this is a lot, and we have a lot of wonderful TAs supporting us, and we're going to show those names and applaud those guys, but things may change, so really bear with us. That's the thing. As Yoda says, always in motion is the future. So keep in mind as the... All right, very good. Hot off the presses. How many people on the waiting list? Raise your hand. Raise your hand high. You're not on the waiting list anymore. We just added a 10th section. Let's have a hand for Michael David, who added the 10th section. All right. We now have 300 people in this class officially. So your job, by the way, all of you, is to consider moving to Lab 105. Right now, only 7 of you are waitlisted for that section. You're going to be immediately added to that so that you're all set. Those 7 who are waitlisted for 105 are immediately in. We put it for the time that was the most popular for the students. However, only 7 move over, then that's pretty much an empty section. The other ones are going to still be full. So everyone else has to think about how can I consider the guys in gray? And the 105 is the new section in gray, which is 10 to noon on Wednesday, and the discussion is 1 to 2. So if you can make that from any sections, right when you're on campus, not an evening thing, please move to that section because we now have 23 open spots that you should all move in to make room for the people who are waitlisted for your section and can only make your section. Does that make sense? Okay. Is there a pointer?
Yeah, the dot right there.
The dot. Oh, no. Is it right here? Was I give you LASIK. I'm going to give Mike LASIK is what I'm going to do. Very good. So, very good. Course information. So here, there's a website. You know this. You guys have been around EECS for a while, so you know that's the deal. We're the instructors. We have 7, I guess now. 7 awesome. Can the TAs stand up? Let's get the TAs in the house. Get some love for the TAs in the house. Folks, these are amazing people. Raise your hand. That's awesome. Sean, Paul, Eric, Ian, and Ani. And I guess Brian is at a wedding, but he'll be here. He's our head TA. So these guys are awesome. They're the best in the department, so we're really pleased with that. We got 3 textbooks that are critical. Patterson Tennessee 4th edition, not the 3rd edition or anything below that. And don't get the Asian version, which is like I think an illegal duplication with not anything against the Asian folks, but they happen to make an illegal copy of the book and don't get that one. The C program language book is like 1985 or 89 or something like that. It hasn't changed forever. The C hasn't changed forever. We are going to be using the C99 extensions to C, but that's not an extra book. That's just an extra little flag you've specified to the compiler. And this wonderful Data Center of the Computer book, which we'll have as a free PDF, I believe. So you really only need these 2. By the way, every good programmer worth their salt who's ever done C has this book on there. I mean, it's not like, well, you know, I had this AI book or this AI book or Patterson's book or some other book in computer organization. There is one. It's like there's one book to rule them all. And that's the book we have. We call it KNR. Every programmer calls it KNR, Kernighan and Ritchie. It's awesome. Piazza. How many people like Piazza? Raise your hand. Is that awesome or is that awesome, right? In the olden days, we had news groups and facts. I am so sold. In fact, if you go to the Piazza page, picture of me going, yay. So go Piazza. We love this. Everything happens there, folks. Everything happens there. Our announcement blurs go out to you. You talk to each other. You teach each other. There's massages. There's something happening in Piazza for everybody. Work with that. All right. Oh, yeah, sorry. Let's mention this. There's a textbook rental option, which we'll have on the website as some information. So if you actually don't want to buy it but want to rent a textbook, interesting kind of model. I guess you could rent cars or have zip cards. This is kind of like zip textbooks. You have it for a semester, and then you give it back. OK. So here's some reminders for the topics. If you want to switch, every single section, except for the new one we just added, section 10, is totally packed. So we can't just have everybody say, oh, I think I'll ignore what Telebear says, and I'll run to the section right after lecture, because there's no way. We only have 30 machines and a finite amount of lab assistants and TAs to make that happen. So you really have to stay in the section you've told Telebears you're in. However, if you find another person, like kind of a dating service, who wants to swap with you, then you can actually swap. And we're going to set up a Piazza thread A single thread in Piazza will manage this entire process. Well, you will declare, I'm in lab 14, and I want to move to lab 12, 9, or 12, 37. Then somebody who's in one, I don't know what to make them, I should make more numbers up in advance. So then they, if anyone ever in those sections but want to move to yours, they just say done, and you just edit the post. You know Piazza is a wiki, right? You just edit the post, you send the mail saying, hey Bob, I want to switch with you, done, edit the post, it's done. You guys are now swapped officially. It's amazing. Don't tell us at all. Just make the swap, tell your TA, I'm now Bob, and you're now, so that they tell your TA so they know, and that's fine. We are going to have partner work. In the past, people have said no partner work because we want to make sure that students get their programming chops through the lower division and don't kind of ride on the back of other students before they get to the upper division where it really is, trial by fire. So they have asked us, students at the HK and IEEE student feedback to the faculty every year, they said, don't make the lower division have partner projects so people can really get their stuff and not just kind of, well, my partner was smart and hated the project because I was busy watching the Super Bowl. So that's not good. So what we've done is they suggested don't have any partner projects. But because two of these projects are going to be so cool, so massive and awesome, read hard, what we do is we have allowed you to do partner work for those two. Is that cool? So when you go to the Amazon cluster, that's hard, partner work, and that's awesome. And when you go to the multi-core stuff, that's hard, and that's with the partnership, all right? So already start thinking about, only, by the way, two-person partnerships, so already start making your buddies of who's going to be partners. So already, everybody start hooking up right here afterwards. Wait, not the new world of hookup, but partner hookup is what I'm, Ouch, you got to watch out what you say now. Okay, so course organization, this is the grading standard that I've had forever with a small modification, which is basically labs are not worth a lot, just like the Brian Harvey model. Labs are where you're learning, right? You cannot have labs be a place where there's a lot of pressure. Labs are where your mind is fuzzy and you're getting it clarified from fellow students. I just posted on Piazza that I do want you to work on your own lab, but I want you to get help from everybody, right? Talk about labs all the time. Eventually submit your own and get credit on your own, so you're still making sure you do it. But talk a lot. I want talking amongst everybody in lab. It really should be a wonderful thing. If you all burst into song, that's also fine too. So labs is 5%. Projects, a reasonable amount. Midterm and final. The key thing about a midterm, only have one exam, one midterm and one final, and you can clobber it. Love that. If you do better on your final than you did in your midterm didn't happen, and your final is your midterm grade. With that one? Let's get some love for that policy. That's what I'm talking about. That is what I'm talking about. Does it work the other way? It's a very good question. And we've actually had, can you believe I've actually had a student who said, yeah, I didn't take the final. Why? Because I did well in the midterm, and it clobbers the other way. No, it doesn't clobber the other way. And yeah, not so much. So peer instruction has been amazing. We love and bless peer instruction. It is students teaching students. It's also a great time for us to get feedback of whether you get something. So right now I might say, tell me a little bit about what that third big great idea was. It starts with this two letters, and what might it be? And you have a little multiple choice thing, and you then would vote on that, whether you got it or not. Or we can ask an even more detailed question, do some mini calculation in the back of your envelope, and come up with that, as you saw in the example about the number of the failure rate of those disks. So we're going to have that. The way it works is we'll post a question. You will all have either a clicker that you buy and can sell back to the bookstore when you're done. You can buy it used and sell it back to them. Delta's about $10. It really isn't a big deal in terms of these clicker things. Or, I just set the course up to be web clicker enabled. Raise your hand if you have a smartphone, either a Palm or a BlackBerry or an iPhone or an Android. Raise your hand if you have that. You folks can use your smartphones to vote. Is that the coolest thing? Love it. This is what we call eating your own dog food, because it's going to a data center, right, and it's coming back, and it's coming to here, right? So you get it? The whole meta. Yeah, you have a question over there. I don't know whether it's Wi-Fi or data. Somehow you need to talk to the web to make the connection. It's a little app that talks to the web. So I think in this room, both of them, actually. I think either one would work. If you are not getting signal, but you have Wi-Fi, it'll work. If you validate with Airbase, it'll work. Or if you have signal, it'll work. Either way. So all you do is you go online, you go to Clicker, you sign up for a thing, you pay. The minimum, if you want to do a minimum, is like a $10 deal for the semester. Or you can say, I might use a Clicker next semester, so you can buy like a year for like $15 or something, right? Or you could say, maybe I'll buy for 2 years for like $22. So it's like a nice price game where rather than paying $10 every semester, you can be cheaper if you think you're going to be using clickers next semester. Whether you know that or not, who knows who's going to know those answers. But nevertheless, the very minimum, it's only $10, which is a great deal. Better than 40, which it used to be in the olden days. And if you drop your cell phone and get a new cell phone, that's still valid because they have your account. It's not tied to the particular device. Unlike the clicker, you buy a $40 clicker, you step on it, the truck rolls it over, you've lost $40. So watch out for that. Or avoid trucks. The ECS policy, this is an absolute graded course. I don't want any competition. You know what happens if you amplify and turn up the knob to 11 of stress for students in curve-based courses like, I don't know, pre-med? You know what they do? They go to the library, rip pages out of the books. Have you seen this? They will effectively try to hack other people's accounts so that they can't do well, because if I can make this half of the class do poorly, then I'll do better myself. That's the worst thing. I never want to have that. So this is an absolute graded course, as it is in 621A, B, and C. That said, we also have the issue of trying to make sure we don't have grade inflation. So I can't give all your A's, even though if you actually do get all A's, you will get all A's. Isn't that cool? So if we actually lay out all the exams and projects and turns out you all get A's, guess what, folks? You are getting A's. Huh? For that one? Love. Let's get some love for the absolute graded course. There we go. So it's cooperation, not competition. That's critical. And it's critical because, let me just go back a couple of slides. This is something called EPA, and part of it is altruism, helping your fellow student. There are points that you will get on the 100% for helping your fellow student for that. That'll come, favorite. Favorite also. You can reserve your comments to your favorite or to your fellow. So this is just basically to see that we don't have grade inflation and the average is a B minus. So we're going to try to tune the exams and projects so that the average is a B minus, and we've been very good at doing that in the past. Extra credit APA, and make sure I have enough time to kind of cover these things. Perfect. Look at this. Oh, I love it. Love it. All right, I have enough time. So EPA is not about the protection agency. What this is 3 students in the past have been incredible. And I wanted to be able to honor these students for doing incredible work. I had a student named Nishant Prasad who was in CS3, and he was the best student in class. But not just the best student in class, he would come, and he was the only guy in office hours every week. And he would come in and say, hi, Nishant, again, I know you're Nishant, you come every week. And then he would say, can I have the hardest problem you can give me? And he would ask for that every single week. And I was amazed. And at the end of the year, I wanted to give him some points for he was the only guy in class who was doing that and really showing this effort and visiting me. And I couldn't. I had no official way of doing it. So that's the effort part of it. Participation is, I used to have somebody named Jesse, and I've since forgotten his last name, but Jesse was in 61C with Dave Patterson in Wheeler, which is this big, huge, echoic auditorium. And Dave would be up at the stage, I'd be on stage, rambling, going fast, and we'd be losing people or going and saying something wrong. And only Jesse had the chutzpah to say, are you sure that's right? And no one says it to Professor, but he said it. And I said, hey, you caught me. That is wrong. Thank you so much. And throughout this, and everybody else in the class is going, shoo, thank you for asking that. I was too scared, but he did. Okay? And every single week, he would raise his hand, and he would be like the class pulse. If Jesse got it, the class got it. If Jesse didn't get it, the class did. It was amazing. I wanted to have a way to give Jesse points, and I had none, and now I have some. Because he was raising his hand, he was making lecture more interactive, he was awesome. So there's that. So attending lecture, voting. The nice thing about the voting in clickers is if you buy into the drink the lemonade and do it, I will get feedback from the entire class, whether you're getting it or not, stop and back up and explain it more. So I need you all to do that. You don't have to. You can volunteer to do whatever you want to. But if you do, I will give you credit, official credit in those 5% for doing that. So please do come in and vote. Yes, question? Can you give him credit? Yeah. Give him some credit. All right, go ahead. No, go ahead. Go. Great question. That's an extra point for you. So it's like, what's the stand-up comedy thing? Whose line is it anyway? Is that what it is? 1,000 points for you. No. So the issue is whether we care about what's right. No, I only care that you vote, to be honest. Although at the end, it might be fun to see who had the highest percentage, but no points in terms of that. Just vote what your heart is. That said, don't mess up. Don't be smart. Try to be good, but do the thing. This is so much fun. Altruism. So, as I said before, I want you guys to help each other. So I have my TAs, as they're helping people, if I see somebody else answering questions regularly, at the end of the year, I want us to make sure we give that person credit, and that person is going to get points at the end. Also, Piazza is an amazing online, asynchronous way for you all to help each other. And guess what? When you respond to a post and have a student answer, I know about it. There's a way in Piazza to track that, and I will use that in calculation for your APA. So if you are helping people and clearly doing that, then I will give you points for that. So try to help each other rather than just post and never help. Try to give answers too when you have them, okay? Great stuff. So here's the key. APA will bump up if you have, you all start with kind of like 1 point in APA, which is enough to give you 5%. But if you do more, you can bump more to that. So you kind of start with a little bit of that, and you kind of bump to max, and you can even exceed 5%. If somebody's actually amazing and done 7%, I will give you 7. I will give you kind of extra credit for APA. Here's the key thing. I never want anybody to say, what's my APA score? This is about like a meta level of what, the worst thing is like somebody grade mongering. No, I should have gotten the 3 versus 4. I don't want that. So it's internal. You can never know your APA score. Just trust that we'll do the right thing. We'll have all the data from the clickers and from the Piazza and from the TA's numbers. Those will all be good, but you can't ever see it because I don't want you kind of complaining about it, okay? All right. Almost done. Slip policy. So the slip days. So if you are late, everybody, including me, has an emergency that comes up every once in a while, right? I got 2 kids. One of them gets sick. I can't make a deadline because I had to be with my kid at home because he was sick. So you have the equivalent of those things, right? You get sick. You got family emergencies, all that stuff. So rather than have to always ask, hey, Dan, hey, Mike, hey, TAs, can I have a special thing because of this situation, that situation? I said, how can we eliminate all that conversation and just give you enough spare currency that'll be automatically spent for you if you hand in a late assignment? Enter slip days. So slip days is the idea that you don't do anything different. You just hand in your assignment, and if it happens to be a couple minutes late or an hour late, then once you eclipse the exact deadline, which is midnight, once you eclipse that, and it'll depend what particular day, depending on how we do the thing, but it'll always be midnight, so I don't want you staying up all night. We used to have deadlines at like 4 a.m., and guess what? Everyone would stay up to 4 a.m. So we said, get a good night's sleep. Midnight is a nice time, so it cuts off midnight. So if you happen to submit it, like you can't get it done, and you just fix the bug at like 12:10, well, one question is, well, I only used 10 minutes. Can I get that back? The answer is no. You might as well, if you can't get it done by midnight, go home. Don't keep working, because let's say 12:10 really turns into 1:10 and 2:10 and 3:10. No. Once you've gone past the day, you're going to be charged a slip day. So just go home and get a good night's sleep and try it the next day. That's the reason it's slip days, not hours. Because then you'll go home. At slip hours, you're like, oh, I don't want to use up another hour. Oh, I'll stay up. No. I want you guys awake for your next day's classes. You'll end up burning through next day's classes asleep if you stay up all night, right? So I want you guys getting good, healthy sleep. I want you eating your broccoli. I want you doing all that kind of stuff. So slip days. So you have these 3 tokens that will be automatically deducted from you. And once you run out of those, then every time you're late a day, it's like a third off. So basically, it's 3 days. So 3 days afterwards, which is kind of the max I can ever be late, that's when the primary assignment is worth 0. That makes sense? You kind of lose a third once you've used your slip days up. But we'll automatically deduct a slip day for every time you're late. I would save them for projects, which are worth like this much, and homework's worth this much. So save them for projects. Question in the back. Slip days total. Here's 3 coins. Bing, bing, bing. It's automatic. It's not per project. That's a good question to ask. Yes?
For the team project, do you deduct?
Yeah, the team projects, you both get deducted, and you both have to have the currency to work. So it's kind of like, I take it from each of you, because it's like that. Yes?
Since you're automatically deducting it, you can't say, I don't want to send it on homework.
That's a great question. That came up in the TA. The answer is yes, if you say, I'm late a day on my homework, but I really want to take the 33% hit for that one for my homework and save it for the projects. You can do that, put it in your README file. Does that make sense? So you can save it. If you're late on a homework and you don't want to use it for the homework, just send us mail saying not to use it, and we'll reverse it, and we'll take the points off that. Okay? Good? Excellent. All right. So this is where it gets heavy, and we all did the thing. You guys are all honest people. You got to Cal. You worked hard. But stress is going to get to you, and you may resort to some, unfortunate practices in terms of sharing work. So here's the rules. I'm supposed to show this. The ombudsman says always make it very clear what your cheating policy is so that nobody ever asks you or it wasn't clear. It's clear. Here it is. You can never copy solutions from other students. If you ever do that, both giver and receiver are equally culpable. The penalty for that is negative points for the assignment, because you're thinking like, okay, I didn't do my homework. I could either copy from this person or not. The answer is you should say not. Just take the hit or take some slip days and try to do it yourself. But if you copy, then you were going to do 0 because you did no work, right? But if you copy and I get you caught, the penalty can't also be 0 because that was the same as before. So I have to give you negative to have a disincentive to not do it in the first place. Does that make sense? So you get negative points for if you get busted, and you lose all your APA, which is a lot of points. So you'll go back at least maybe a half grade, maybe to a grade on that. That's serious. So don't copy, folks. Here are the rules of what means copy. Also, obviously, don't post code on Piazza, right? If you need help, you have to kind of ask it in a way that doesn't reveal the answer to other students, because what you're asking for might be the aha that we're trying to get you to get to. So please think twice about the questions you ask so that you don't reveal the wrong thing. If you're unclear, just ask somebody in person, right? What did you do about this case? And I can't stop that one. So asking somebody in person about a particular bug you have is much safer than if you're worried about the question of, is this the big aha to reveal on a project? So be cool with Piazza, too, is what I'm basically saying. So if you look at this, there's a great article from San Francisco. It says here, this is about digital data and living in the digital world with all these devices, 3 o'clock. And what it says is, if I go forward, scientists point to an unanticipated side effect of having the digital world, life. When people keep their brains busy with digital input, they are forfeiting downtime that could allow them to better learn and remember information. So I take from that, and this is from UCSF, so I take from that once this course happens, don't immediately go away and just text and tweet and do the thing. Let this stuff settle in. Like, as you're walking away, process what you just got from this class. Talk to your friends about those 6th grade ideas and which means most to you, or which you think is the most important. Or if you went back in time 10 years, which do you think was there 10 years ago? Kind of think about it and try to internalize a little bit. Do that with every single class. That's what I'm trying to say for this. So, also, there's a little bit of getting, this is what's happened now. We're at 60. We're going to run this in general where we do an admin break halfway through to kind of wake you up for your lecture. Okay? So in summary, you've seen 6th grade ideas of computer architecture. We're going to hit those overnight. This is not the last time, certainly. We're just giving you a taste, like a little buffet, a little taster, like appetizers. We're going to jump in hardcore to all 6 of these ideas. You're going to come away internalizing these. If you want to have a tattoo with these, that's also okay. We'll see you guys on Monday. Buy your clickers. Buy your clickers. All right. Woo!